Okay, so this lecture is on what are called bandits. So bandits are an example of a topic called reinforcement learning, okay, which we'll talk about in a little bit. So the name bandit comes from like a slot machine in Las Vegas, right? So who here has been to Vegas and pulled the arm on a slot machine? You all need to live a little bit. All right, so basically a slot machine, for those of you who don't know, is like this thing. You used to have these big things that were, and the appeal of the slot machine was that it had this big arm. You would yank on the arm and the reels would go around and you'd see what you won, right? And so it was called a one-armed bandit because it was like a thing that took your money with only one arm, right? And so this idea of pulling the arm, and so the other thing about bandits is I always do this like arm pulling gesture, right? So here's the idea. And so the idea is that you have several different options that you could choose from, and you are investigating these options and eventually trying to find the best one, right? So let's suppose that we have a two-armed slot machine. You don't know anything about this machine. You don't know anything about what's inside of it. All you can do is see what rewards you get when you pull on the arms, okay? And so let's suppose that we take 10 rounds of this slot machine, and we have like the left arm and the right arm. And I kind of, in the beginning, I just randomly choose which arm to pull as long as I pull both of them 5 times, right? And let's suppose that these are the rewards I observe in dollars. Okay? And so these are rewards. And so if I look at this table of data, what I might conclude is that the left arm seems to be doing slightly better, right? The expected value of your payout is, $4, whereas the expected value of the payout on the right arm is $2, right? And so say I have 10 more pulls of these two arms. What should be my strategy, right? So one policy would be to say, okay, just keep on pulling the left arm because that one looks like it's the best one, right? Just totally ignore the right arm. The other argument is to say, well, the right arm may just be having a bad day, and maybe if I pulled that a few more times, I would find out that it was actually pretty good. So how many more times should I pull it? So if I have a finite horizon for how many times I pull the arms, this is what bandit algorithms are all about, is thinking about, okay, so what is my strategy for what's called exploration, trying to find out what's going on with these multiple options, versus exploitation, which is taking the best one and just playing that one for as much as you can, right? And so that kind of tension between exploration and exploitation is what makes bandit theory interesting, right? So the idea is, key concept is exploration versus exploitation. And so applications of bandits come up all the time, right? And probably ways that you're not necessarily very familiar with, but not familiar with, but very aware of, let's say. So one big example, I think, is like what you call A versus B testing. So if you've ever been like a website designer or a developer, you may be unsure about how you should design your web page to maximize clicks or maximize, Amazon wants to maximize the probability that you buy this item, right? So maybe the option is to put the buy it now button at the top of the page versus the bottom of the page, right? So what they could do is they could run A versus B testing kind of protocol where people are presented with the buttons in different places, and the payout in Amazon's world is, does the person buy the item or not, right? And so obviously they want to converge to the thing that gets them the most profit, and they're experimenting on you, the user, to see what the rewards are, right? Now this is kind of like a cynical commercial kind of argument, but the other thing that you could think of that would be much more meaningful would be medical trials, right? So medical trials, clinical trials are the kind of situation where you've got a set of drugs that may be effective in treating a patient, but you don't know how effective they will be, right? And so, there's these very specific protocols for how you can deliver clinical trials, but the idea would be, okay, we're going to kind of keep on giving people different treatments, but hopefully converge to the treatment that is most effective for the patient, right? Although let me be honest that I'm not really sure that bandit algorithms literally are being used in any clinical trials, because I think the subtlety of the theory is probably a little bit too much beyond the ability to convince a bunch of policymakers about how they should deliver clinical trials. But it is a very interesting idea, right? there's kind of like a combinatorial aspect of like, not just, like which ads should we show the user on a web page? Again, I don't want to make it seem like it's all about e-commerce, but that's one possibility. Netflix is using bandit algorithms all the time to think about, I only have, 4 big slots in my kind of, we think you'll like kind of queue that has real estate on the front page of my Netflix page. What 4 things do I show the user in the hopes that they will kind of watch one of them? So again, the reward for Netflix is user watches the thing that they are presented. Otherwise, those 4 things are just kind of like wasted, right? From a more engineering perspective, it's kind of like, what path should a packet take through a network? Right? So for example, to send packets from Albany to San Francisco, there are many possible paths that those packets may take. And so I want to find the best one, right? But I also don't want to leave out the possibility of there being even better ones I didn't explore, right? So eventually I want my packets to kind of be converging down the same route, but in the meantime, I'm trying to figure out which is the best route, right? So it's kind of like a network throughput thing. And again, you can imagine this is kind of like, a graph kind of algorithm, right? Because there may be like a kind of a geometrically branching sequence of paths, and evaluating them all may be tricky, right? They're kind of like what you would call like these weighting algorithm things, which is kind of hard to understand immediately, but like, they're called weighting, problems. Like for example, you could, wait for the bus that will take you to campus in, 3 minutes, but the time the bus takes to get to the stop is variable, right? You cope with this problem all the time, right? Or you could just walk to campus, it'll take you half an hour, but you have like kind of this fixed cost, right? So in some sense, you're always kind of trying to optimize, should I wait for the bus not knowing exactly when it's get there, or should I take the sure thing, which is getting to campus in half an hour, right? Also, you may have heard of this Go playing computer called AlphaGo. And so AlphaGo was an algorithm that generally involved reinforcement learning, and more specifically involved the Bandit algorithm and how it decided how to do a certain kind of tree search that was a core part of the algorithm, right? So these kinds of game optimization, like these game playing algorithms, are often reinforcement learning type algorithms. And so more generally, game, I don't know if I call it game theory, but like just game algorithms in general often involve this kind of idea. And finally, as something as simple as, like I've got a friend who's in France right now, right? So she has, a week there, which means she's got like, 20 meals, right? And so the optimization is like, should you go and try some new food that you've never had in the hopes that it's going to be amazing? Or should you stick with going to McDonald's where the food is going to be reliably good and you're not going to be challenged? And so you got this horizon of like, how much should I explore and how much should I commit, right? So in general, you can think about a lot of ways to map real world situations that you have onto this kind of idea of explore versus commit, right? And so let's talk about some basic terminology in bandits, right? So let's set up the problem a little more mathematically. So terminology for bandits. So a bandit problem is a sequential game between a learner, that's you, and an environment, which is the hostile world you live in. And so basically the idea is that there are n rounds of playing, right? And that number n is called the horizon, so that there are n rounds of play. This is called the horizon. And in each round, let's call round T, the learner an action, A sub t, from a set of, finite possibilities. And once they've chosen that action, the environment reveals to them a reward. R sub t, or let's call it X sub t, sorry. And that reward is a real number, like a number of dollars. Okay. And again, these finite set of possibilities, these actions, are kind of like what we call the arms of the bandit, right? Those are my options. And so the fundamental challenge is that the environment is totally unknown to the user, right? They don't know anything about the environment other than what it reveals to them by giving them rewards for different arms. And of course, the learner can't see the future. All they can do is see what they've done so far and then decide what to do next, right? And so, so the learner, has to choose their next action, AT, based on the history so far, which is kind of like, what do I know up to point T? I know the action and the reward I got on turn 1, the action and the reward I got on turn 2, the action and the reward I got on turn T minus 1. And then the last step is what's called a policy, okay? So, and this is the most important kind of word in reinforcement learning. So a policy, pi, is a mapping from history to action that the learner uses. Right? So the learner is basically got a recipe or an algorithm that says, okay, here's what I've seen so far, here's what I should do next, right? And what is the learner trying to do? The goal of the learner is to maximize their total reward. So over all the rounds, they want to make their reward as much as possible. Okay? And so the bandit setup is kind of a very specific case of reinforcement learning, but this idea of a policy in general, if you do any sort of RL, you will see that word over and over again. Yes?
What is A and X again?
So A is the action that you take. A is the arm that you decide to pull on this round. And X is the reward that you get for pulling that arm, a dollar amount, right? So in the slot machine case, it's like either pull the left arm or pull the right arm. That's the A. And then the X is the $0 or the $10 or whatever. Okay, so the central problem in Bandits is understanding what is called the regret of the user. Okay, so the other big word here is regret. So the regret of a learner relative to some other policy pi is basically, the total expected reward using pi for n rounds minus the total expected reward that the learner collects in n rounds. Right? So it's kind of the difference between, so the idea is that what you do is this pi generally, it's not just necessarily a single policy, it could be a collection of policies, right? Or, policy or a collection of policies, let's call it capital pi. And the idea here is that generally this, includes the best possible policy. Right, so basically the idea is that there is some ideal policy that if you followed that, you would do the best that you possibly could in a probabilistic sense, right? There's always randomness in the environment, but there is something that is like the best you could do. And the regret is basically the difference between the best you could do and what you're actually doing. And so obviously what you want to do is you want to minimize the regret. You want to bring what you're doing to be as close as possible to the optimal policy, right? And so, for example, if I knew that there was one arm that would always do, the best job, then, one way of thinking about this would be like saying, the regret after n rounds would be like the difference between n times the mean for the best arm, right? That's the best that I could do, minus the expected value of whatever I decided to do, right? So this is like saying the optimal arm minus my policy. And of course, the difference is, the challenge is that you don't know what the optimal arm is, right? So if the regret is large, then the learner isn't doing very well. If the regret is small, then the learner is doing pretty well, right? And so there's also kind of like this intuition where you can kind of decompose the regret into kind of like the difference between, the intuition is that we also sometimes define this delta I, which is called the gap between, reward for action I and the best action. So if all the delta i's are small, right, that basically means that all the actions are more or less the same. Doesn't make a big difference what arm I pull because everything is going to be more or less good, right? So if all delta I are small, all actions are about the same. On the other hand, if the delta I are big, meaning that there's a big difference between the good arm and the bad arm, it should be pretty easy to figure that out early on so that I can commit to the good arm faster, right? So should be easy to identify, the optimal arm. So, sometimes we care about, the worst case regret over all possible environments, but other times we're just caring about the regret for a specific environment, okay? And so, there's always going to be some non-zero regret because clearly if I don't know anything about the environment, there's no way that I'm going to be some sort of a psychic and just start pulling the best arm all the time from number one, right? There's going to be some sort of a learning curve of some sort, right? But what I want to do is I want to minimize my regret over the n times I have to play this game, right? And so, the core question that people care about with bandits is, how regret, Rn, grows with n, right? Question?
Could you explain again what the mu represented for what that represented, and also what the delta was again?
So basically, there is, in my possible arms, there's one best arm, right? And the expected value of pulling that arm is mu star, okay? And if I knew what that arm was, I would just be pulling it all the time, right? And this delta I is kind of like the difference between the mean of the best arm and the mean of the arm that and arm I, right? So for the best arm, delta I is 0. For any other arm, delta I is positive, right? Because there's some net difference between the best mean and the current mean, right?
How do you know that best one?
Well, that's the thing, is you don't know, right? You as the learner don't know. You're trying to discover it by pulling the arms. And you're trying to figure out, okay, after pulling these arms many times, I'm going to make a choice at some point, hopefully, about like this one I think is the one that is the best, right? So you don't know, right? The environment is a hostile environment, right? It's not giving you any information. You are forced to infer this from your observations. So we want this regret to grow. I mean, the regret is always going to get bigger, right? But I want to have that regret grow as slowly as possible, right? So a good learner has what's called sublinear regret, which is a fancy way of saying that in the limit, the more rounds I play, if I look at my regret and I divide by n, I go to 0, right? What this means is that at some point, the learner has caught on to the best arm, right? Because what I want is that at every n, I want that number to be, kind of on the average growing down. If I'm a good learner, I should be able to figure it out eventually, and that means that on my, as my horizon grows longer, I should be basically picking the right arm, most of the time, right? So this is like saying, the learner chooses the optimal arm almost all the time as n goes to infinity, right? But kind of the question is, and again, this is a very gentle and high-level introduction to bandits, but if you read a book on bandits, you're immediately going to get tossed all of these convergence proofs about what the regret looks like, right? So the kind of core question is how well we can do under different circumstances. How well can we do? Right? So for example, can we get the regret to be like the order of square root of n? Can we get it to be like on the order of log of n, right? Those make kind of big differences in how well I do, right? And so these kind of problems almost immediately get very complicated once you pose them and try to actually give you some bounds. And so in some sense, today, I'm not actually going to give you any real bounds on regret because number one, I don't think it's like super constructive, but like number two, it very much depends on fairly complicated probability and math theory that I think that is not beyond you if you took probability, but would require a little bit more mathematical maturity than I'm in the mood to convey right now. So we have to make some sort of simplifying assumptions to be able to get anywhere at all, right? So for example, if the arms were like changing around all the time or could have their rewards like be a function of time, well, clearly that would be like a super complicated problem, right? So the easiest thing to assume is that the rewards are, not changing, and every time I pull the arm, I'm drawing from the same distribution, right? So, the easiest case is what's called a stochastic stationary bandit. And what that means is that the rewards when I pull the arm are IID, which we know what that means already. And they also depend only on the current action. For example, one easy situation is that when I pull the arm, it generates a random sample from a coin flip that has the same probability of heads every time I pull it. Or it could be a Gaussian distribution that has some mean and sigma, and it draws from that Gaussian distribution, right? That's the most easy situation, is that the arm does this consistent thing. There are more complicated situations where, let me just say, this is kind of like versus what are called adversarial bandits, that, the environment can make the life very hard for the user, right? So if the environment is changing its strategy depending on what the user is doing. Or, for example, if the user knows exactly what your strategy is and it's trying to make life as pessimistic for you as possible or as confusing for you as possible, then life is very hard, right? So, these stationary bandits are much easier to deal with mathematically than these adversarial bandits where really anything goes, right? So what I want to do now is talk about a few simple algorithms that you can use to interact with bandits. And then, again, if you want to learn more about this, then you could take a whole course on this. So actually, Dr. Tajera here is a very well-known expert in bandit theory, if you ever take a class from him. I don't think he's taught a class on bandits, but he could. Let's talk about a couple simple algorithms. So what we're going to talk about now is a few basic algorithms. And so I'm going to introduce these algorithms without analyzing them and going into gory details about what the regret bounds and so on are. I'm just going to kind of tell you what these are, just so you kind of know what the major classes of algorithms are for bandit theory, okay? So, algorithms with an S. So one, kind of common one is what's called explore, then commit. Or ETC. You could apply all this stuff to your dating life also, right? It's like, how do you know who's going to be the one, So basically, the idea here is that you play each arm a fixed number of times. And after you played each arm, like say M times, you choose the best one and you just keep on pulling that arm forever, right? So the idea is to play each arm a fixed number, let's call it M, of times, and then commit to the best arm, meaning the one that has the highest mean. Right? And so again, you only have capital N tries total, right? So the idea is that basically, this capital N is like saying I have, M times, let's say, K pulls, right? So if the K is basically the number of options or the number of arms, this is like the exploration phase. And then the rest of it is basically the exploitation phase. So I'm using up, M times K tries in exploring the space, and then whatever I have left over, I'm going to exploit, right? And so clearly, there's a big trade-off in how I should choose little m, right? So if little m is too large, I basically spend all my time exploring, and then I have very few tries to actually exploit the best arm, right? So that's bad, right? So m too big means that, I explore for too long, and I have not enough time to exploit. Conversely, if m is too small, so say that I only pull each arm once, right? That's a pretty, noisy estimate of what each arm's mean could be, right? We know from probability theory that if I were to, average a bunch of draws from the same distribution, that eventually I will converge to the mean of that distribution, right? But if I only get one draw, well, then it's probably not so likely that that will be a great representation of the mean. So the problem with this is that, say I just did one, pull for each arm, then I might commit to an arm that's actually not the right one or not the best one, and then I would never know what I missed, right? So basically, m too small means, probability that I commit to a suboptimal arm is high. So, it's always a problem, right? And so there are a bunch of theorems that have to do with, if I have the fixed horizon capital N, how should I choose M to do the best that I can, right? And so one result basically is that, there are theorems that show how to choose M as a function of N to achieve this kind of, good asymptotic regret, right? So for example, you can find a formula that tells you what I should do, and then the regret will be on the order, of n to the 2/3, right? So if I look at that, if you're a CS person, you know that this will, if I divide by n, go down to 0, right? So, this is not a bad result, because no matter how crazy different the arms may be, I could show that I can achieve sublinear regret with a recipe for how to choose M based on N, right? Now, there are definitely a lot of variations on this theme, right? So one thing, and again, if you think about how this could be applied to something like medical trials, you can see how relevant it would be, right? So for example, I've got 1,000 patients and I've got 5 drugs and I want to give the best drug to as many patients as possible. How could I do that in the best way, right? Now, in this explore then commit kind of framework that I told you, you're kind of forced to pull all the arms M times before making your decision, right? But, you can imagine variations on this where you could stop early, right? So let's just say that variations on this theme are, the learner can decide to stop exploring, some or all of the arms once it's confident enough, right? So, for example, maybe I try each arm 5 times, and I'm like, okay, well, this arm clearly sucks. Probabilistically, there's no way this arm could be amazingly better, right? And so I should just throw that arm away and concentrate on the other ones, right? And so this is, if you took probability with me or with anybody, you can remember the stuff towards the end of class where we're talking about things like confidence bounds in, if I get an average of n measurements, how bad could it be compared to the true mean, right? That's one reason kind of why we care about those kinds of bounds. It's like, okay, saying, well, clearly I can statistically say this arm can't be better than these other arms, and so I should throw it away, right? So there are, definitely more complicated setups where you can start to rule out arms early on instead of being forced to try them all, right? And keep on trying them all, even if you're pretty sure that some of these are bad, right? Okay, so that's algorithm number 1. Comments or questions? Yes?
So if you're just trying each arm in optimal amount of times such that you can accurately find what's the best arm?
Right, so basically it's like saying, there's a recipe for how I should choose this little m based on this big N that, probabilistically, statistically does the best, possible thing. I mean, you can never be 100% sure that you've gotten the right arm because there's always probability involved, right? You could always get some sort of a freak sequence of, particularly good rewards from one arm when it's actually not that great, right? But as I pull the arm more times, the odds of that happening get smaller and smaller, right? And so, yes, so that's the idea is that, how do I see this, decide on this, and then apply a formula for, that, right? Yeah. So this is, very simple idea, and a lot of algorithms, are still based on this idea. There's also an algorithm called the upper confidence bound. UCB. And, so whereas before we were only looking at the average, the sample average from my observations, right? The upper confidence bound is something where we have a little bit of what's called optimism, as a mathematical term, optimism about the world, right? We kind of say, okay, if the environment was as nice as is reasonably possible, what could the upper bound on the mean for each arm be, right? So the idea is the following. So it's based on the idea of optimism in the face of uncertainty, which again is a good policy for life also. So the idea mathematically is we act as if the environment is as nice as plausibly possible. That is, you assume that the environment is not pathologically out to get you, but that it is generally not doing anything that is worse than average, right? So kind of the idea is I'm still going to be doing this idea of trying out different arms, and then once I pull the arms and I think about my model for each of the means, I'm going to say, okay, I take what my sample mean is, and then I have kind of like an upper bound on how big I think the mean could possibly be based on my observations, right? So kind of the idea is to, assign each arm a value, and this value is called the upper confidence bound, the UCB up here, that with high probability is an overestimate of the arm's true mean. So kind of what we're going to do is, let's suppose we have like 3 arms. So it's like saying, I have arms 1, 2, 3. So what I want to do is I want to take the, say these are the true means, like this. Then my upper confidence bound is, basically trying to say, well, after I've observed the data, the mean cannot be possibly any bigger than this, right? So these numbers here are basically like the mean, so basically, let me write this down a little bit more mathematically. So the UCB is equal to the empirical mean from, the pulls I've made so far, plus a little bit. And that little bit is called the exploration bonus. And so the little bit part is mathematically complicated, right? Like how much should I add to each of these observed means, right? So kind of the idea is that, in the beginning, I might want to be a little bit more generous, right? So if I only pull the arm once, then my confidence bounds on what that mean should be are pretty wide, right? Which means that the, kind of best case scenario for where the actual mean is could be quite a bit higher than what I actually observed, right? Whereas if I pull that arm like 15 times, well, then my exploration bonus should be pretty low because I don't think that I'm going to be wildly outside the sample mean, right? And again, this is all stuff that comes from that last month of probability class, right? The law of large numbers and central limit theorem and all that stuff kind of comes into play here. Confidence bounds on what is the bound on X given n observations is something that I remember doing a fair amount of towards the end of my probability class, at least. And so the algorithm is kind of then basically similar to the previous one, except all I do is that at each pull, I basically choose the arm with the highest UCB and then I update my bounds. Right? So at every pull, I make an observation, I adjust what I think that arm could be doing. That means that these red dots are going to move around a little bit, but I'm always just going to be taking the one that has the biggest, possible mean, right? And so it's kind of a neat kind of adaptive algorithm because I'm not necessarily committing to a single arm and never going back, right? What you can kind of think of is that every time I pull an arm, I'm updating the values of these red dots, and maybe if this one looked good for a time, well, after I pull it some more, maybe this will kind of come back down and say, oh, actually, well, this one now looks pretty good, so I should pull this one, and maybe this one goes up. So that's the idea, is something where you're kind of just always taking the best current UCB, right? So it's kind of a clever idea. And so, the idea is that we should only play arms if their true mean is reasonably larger than, other things that we've played a lot, right? So I shouldn't take some sort of flyer on some arm that I've never pulled, or that I haven't pulled very often, unless there is some sort of reasonable probability that this actually could be great, right? But of course, the more stuff I do, the more information I have about all the arms, right? Okay, so hopefully that makes some sense, right? Kind of a simple idea. Okay, so third algorithm is kind of more related to what I said earlier were adversarial bandits, right? So these, explore, then commit, and UCB are kind of like in the world of assuming that the environment is, stochastic, stationary world, right? Where the environment is not trying to screw you over, right? However, you could imagine that, you're playing some game with your friend and you tell your friend exactly what your policy is going to be, and then your friend, chooses the rewards in such a way that, are going to make you lose out, right? So if the environment knew exactly what you were going to do, clearly it seems like there's no way for the learner to win, right? Well, that's not 100% true, and the reason it's not 100% true is that, the policy that I choose does not need to be deterministic, right? It doesn't need to be the same algorithm every time, right? So what I could do is I could randomize my choice based on, something where now the environment doesn't necessarily know what I'm going to do, right? And so has anyone ever taken, there are randomized algorithms classes here, like didn't Dr. Anshelvich or someone teach one of those? Anyone ever taken a randomized algorithms class? All right, well, let me be the first to tell you then that basically, in the case of adversarial bandits, man, I gotta tell you that this heater is supposed to be like 80 degrees right here. In the case of adversarial bandits, the learner generally has to adopt a randomized policy. Right? So that is to say that instead of looking at this history and producing a single prescription for what arm to pull, one way to think about this is the learner always has like a probability density mass or a probability mass function over the arms and is sampling which arm to pull next out of this PMF, right? So the idea is that, the learner is sampling which arm to pull from a constantly updated probability mass function, right? So maybe initially, this mass function over the three arms may look like, 1/3 on each, right? And as I go on, as I identify the good arms, hopefully things will look like this. But that doesn't mean that I'll always be pulling arm number 1. I may still occasionally pull arms number 2 and 3 because things are random, right? And in that way, I can kind of get around a environment that is really being mean to me, right? So the algorithms here are definitely more complicated to explain, right? But let me give you kind of like a flavor of one of them, right? This is, again, very hand-wavy. So, one such algorithm is called EXP3. And so the idea is that, if I let this number S sub ti equal the total estimated reward by the end of round T for arm I, then I form a PDF or a PMF over the possible arms where it looks like this. And again, there's a lot of notation here that I didn't define, but that's okay. So this here, first of all, forget about where it came from. This here should remind you of something, right? This is a softmax, right? So it's kind of like saying that, what I do is I basically have some sort of expected rewards for each arm, and I normalize those awards into a PDF or a PMF. And this number here is what's called the learning rate. So the idea is that if the learning rate is small, right? So if my learning rate is small, then the result is that this probability density function is kind of like a uniform distribution. If it's a uniform distribution, that kind of corresponds to exploring the different arms, right? If my learning rate is high, then this probability density function is going to be more concentrated, and the result is that most of the time I'm going to be pulling the same arm, which means I'm exploiting. So again, there's kind of like a relationship here to like gradient descent, right? In terms of learning rate, that's also an important issue here. Is what I want to do is probably have a schedule for how do I tune my learning rate so that I'm exploring the beginning and exploiting towards the end, right? So you have a schedule for tuning this rate, and then you have this probabilistic thing. So this is kind of like a very super hand-wavy example of a randomized policy, right, for this. Yes?
What is ST120?
So this is basically like saying, what is the reward that I expect to find out from pulling this arm, right? And so all I'm kind of doing is I'm trying to take these numbers and I'm trying to normalize them into a PMF, right? The same as we do for any softmax, right? So if you know softmax, this is basically the same idea, right? I have kind of a current estimate for how well I'm going to do by pulling this arm, and I just normalize that number according to the softmax function.
And then, why is it again that the small learning rate, when you say P sub t is uniform,
right,
that means exploration, like you want to perform exploration?
Right, so suppose this number was like 0, right? Then the top value would be 1 and the bottom value would be k. That would be like a uniform distribution over the k possible arms, right? So then I would choose basically randomly among the k arms in a uniform way, right? So if my learning rate is small, then the expected rewards themselves don't really play a big role in how I start to pull the arms, right? But as this gets bigger, then I'm basically saying, okay, take the ones that seem to do the best, right? So it's kind of a clever idea. And just in the same way that tuning the learning rate for gradient descent is like a little bit of a black art, tuning the learning rate for this kind of algorithm also, I presume, is a little bit tricky, right? So again, analyzing these things is beyond the scope of just this one introductory lecture, but hopefully it whets your appetite for the kinds of things that you could be doing. Okay. So questions or comments about that? Yes?
For adversarial problems, Jerry, I wonder if you can transform it into some sort of stochastic stationary by like defining a meta problem where like you have a series of actions that you do and you define that as like a new arm and then you somehow like manipulate the reward.
Some sort of meta problem. Well, I don't know enough about Bandits to be able to answer this question, right? So the question is, could you transform an adversarial problem into a stochastic one by kind of like a bigger picture, like going up one level? I'm not sure. Okay. The short answer is I'm not sure, right? One thing I will say, just as a side note, is that everything I know about Bandits, I learned from this book. So let me just show you the book. I think that this is basically like the definitive book on Bandits by Lattimore and Sezbesvari. Sorry for the butchering of this name, right? So this basically has all the details in here. And it's very, mathematical. Let me just say that, just to give you some sense of what I'm leaving out. So, there's lots of immediate math on terms of the regrets, right? So here you can kind of see this is kind of like a key theorem on regret for the explore and commit algorithm, where I have basically, this is the exploration part of, I have m times the gaps for the arms, and then I have what's left over is, the number of pulls I have left times this bound, right? And so, it just kind of goes on like this, which is why I figured it wasn't really that interesting to go through it in class. But if you're interested in reading this kind of stuff, this is the book to look up on. So basically, I think I made a note in the syllabus that this is a free book also, like many machine learning books. So good place to look. Okay, so the last thing I want to say in lecture today is a little more generally problems that are related to this bigger picture of reinforcement learning, right? So bandits are one subset of reinforcement learning. And so another thing that you may see in reinforcement learning is called the Markov decision process. So did I see somebody, was someone taking the Dr. Yell's class this semester? Are you taking it? Yep. So I can imagine that the Markov decision process is a pretty mathematically intense class. And so this is kind of a combination between the reinforcement learning we're talking about today and the hidden Markov model type stuff we talked about last time, right? So kind of the idea is that so the learner is still choosing actions and they're still getting rewards, but they are also observing a state. And the state then transitions, and then that may change what the actions and rewards look like next time. So it's kind of like this adaptive model where the state that you're in is controlling what the rewards are for different actions, right? And so, so the learner still chooses an action and gets a reward, but also observes a state. And then, basically, and then future actions depend on the state that I'm in. So let me try to illustrate a simple Markov decision process, which immediately will become like a mess of arrows and states and stuff like that, just to give you some sense of how this could work, right? So let me try to draw something. So let's suppose that we have 3 states, okay, and 2 actions. So here's state number 1, here's state number 2, here's state number 3, okay? So let's suppose that I can take 2 actions, possible actions per state. And let's call them the black action and the red action, right? So the black and the red arrows here are going to be actions. And then for each action, I basically have a transition probability. Remember we talked about transition probabilities last time. And then I have a reward. Okay. So let's suppose that I'm in state 2. Okay. So suppose that I take the black action, right? The black action could either result in me hopping to state 1 or hopping to state 3. So let's suppose that if I take the black action here, the probability of hopping back to state 1 is 2/5, and I get reward 0. Or with 3/5 probability, I could hop to state 3. Okay. Now, with probability, with state 1, let's suppose that, let's look at the other action, right? So the other action is saying, okay, let's take the red action. With probability 4/5, it drops me down to state 1 and gives me reward 1. And with probability 1/5, it takes me over to state 3 and gives me reward 1. So in some sense, the black action always gives me reward 0. The red action always gives me reward 1. But the other way of thinking about it is that the black action has a higher probability of moving me forward into this state, and the red action has a higher probability of moving me backwards into this state. And let's suppose that state 3 is a desirable place to be, right? So let's suppose that in state 3, again, I have a red action and a black action, right? So the black action, for example, with probability 3/5 takes me to state 3 again, and I get a reward of 10, which is pretty good. And then with probability 2/5, it takes me back to state 2. Whereas the red action will give me a higher reward, say of 12, but a lower probability of staying in that state, versus here, with probability 4/5, it kicks me back down to here. So, and there's also something that I could do for state 1, right? But kind of the idea is that, what I'm trying to do as a game is like try to get up to state 3. That's like the thing that's going to give me the biggest reward, right? So it's kind of like a tension of, do I, take the black actions, which have a higher probability of pushing me forward into the future state, but giving me no reward until I get there, or taking the red actions, which at least are giving me 1 reward every time I take the red action, but are going to push me down back into the lower states, right? So you can imagine there's this tension of saying, okay, so what should I do? Should I try to get myself over into the potential good state, or should I kind of stay in lower states and get kind of like reliable, steady rewards, right? So again, you can imagine that this is a complicated kind of process, but there's still kind of like a way that I could define a policy for what to do at every step based on what I had seen before, right? So, there are many variations on this theme. The math can get super complicated fairly quickly, but I think it's actually pretty interesting. So again, if I wanted to really complete this, I guess I could draw the other arrows, but I think this is good enough to kind of get the idea, right? So more generally, just to kind of wrap up, if we had to define reinforcement learning in general, right? So reinforcement learning or RL in general, if I had to define it, I would say basically it's the subfield of machine learning that designs and analyzes algorithms that learn to maximize long-term reward by taking actions in a sequential context. That's kind of like the most generic, thing. And so the key things that differentiate reinforcement learning problems are, you've got this sequential, game, right? There was no sense of this in anything we talked about so far in this class, right? The other idea was that I'm taking some sort of an action, right? I'm looking at my history, I'm choosing an action, and I'm trying to maximize this reward, right? And so there are many connections between reinforcement learning and lots of other fields of science and engineering, right? So for example, we talked last time in hidden markup models, there are many connections to dynamic programming algorithms. So if you're a CS person, you'll find a lot of dynamic programming in reinforcement learning. There's a lot of work also in control theory. So optimal control theory and what's called model predictive control. Even though control theorists probably wouldn't necessarily think about themselves as machine learning people, they definitely have many of the similar kinds of problems and they use many similar strategies. And so if you took a control theory course, you might find yourself doing some problems that have the same flavor as what we kind of talked about here. Operations research. So for example, in our ISYE department, I'm sure there are algorithms that kind of have a flavor of reinforcement learning that have to do with things like supply chain management, right? So suppose that you're trying to decide, when should I repair this machine, or when should I order new stock at my warehouse in order to fulfill this kind of like random demand, right? As evidenced by things like, game theory, like AlphaGo, there are many, many kind of like, so any sort of like game is like a sequential process, right? And so hence most algorithms that I think are really competitive for kind of solving games are based on RL type of algorithms. And again, even from a signal processing perspective, if you've ever done something like Kalman filtering, even Kalman filtering can be thought of as taking a action in the face of an uncertain environment, right? And so again, if you're interested in this kind of thing, it definitely has tentacles into all sorts of other disciplines, right? To do a real justice to reinforcement learning, I think requires a whole class, which is a good thing that we have one, right? But I did want to kind of at least mention what this is. And again, this probably seems like totally different than any of the stuff we've talked about so far. But let me just say that it's not that different in the sense that, for example, this policy, pi, that's basically a function that goes from the history that I have now to an action, right? That's like an algorithm, right? It's like a input is history, output is algorithm, and this policy could be, deep neural network, for example, right? That is to say, instead of designing the policy, I learned the policy with the neural network after seeing lots of data and lots of examples, right? So there's a whole world of what's called deep reinforcement learning that comes from bringing deep learning, deep networks into this policy-making process, which is why there is a connection between this and kind of the more typical stuff that you've been learning so far. All right, so questions or comments about this? I'd like to hear about what this reinforcement or what this class on Markov decision process is like. I mean, I assume it looks hopefully something like what I drew here, right?
Sure. Yeah.
Yeah.
So we discussed things like that. So it's called decision making under uncertainty, and it is actually a very cool class. And Professor Yale's a very good professor.
Mm-hmm.
And it talks about a lot of different types of uncertainty. So it talks about state uncertainty. We don't even necessarily know which state you're in. Usually the states are more continuous than that.
Yep.
So like you're trying to figure out like, how far from this wall of a room you are based off of noisy information and stuff like that. There's action uncertainty, there's like reward uncertainties, and it goes through like different ways of estimating, modeling, and finding the best route through all of those situations.
Yeah, so that's you can imagine how complicated it would get, right? If the states were uncertain, if the actions were uncertain, if the environment was uncertain, like all these things could be something where you don't actually observe the state. Things could be continuous, right? So yes, so life is definitely a lot more complicated than this. But I think it's super interesting, hopefully, right? And so yeah, so that's my brief tour into reinforcement learning. Hopefully that was interesting. All right, so let me stop recording.